I'd like to welcome you to CIMAP conference and in particular to this pre-session about Laoss simulation software. You brought your laptops, as I can see, so you're interested to play around with the software as well this morning. I would like first of all to introduce my colleagues. Roman Hierstand is the chief developer of the simulation software Laoss. So if there's any bug showing up, you know who to contact. And so he's ready here to help out during the hands-on exercises. And there is Sandra Janac. She's a technical consultant. She's familiar with all the products of Fluxim, but also Laoss, so she can also help you out. And we have some more colleagues of Fluxim here. So I would like to just give you a rough idea of this morning session. I will start with a presentation introducing the simulation software Laoss and explaining what's the motivation behind this software, which applications should this software be useful for. And somewhere halfway in the presentation, we make a short break to start an exercise with Laoss, and then towards the end also some exercise. But we don't have specific script what kind of exercise we go through. Rather, we do it a bit more spontaneously. I will try to show on the computer live some step by step, and then inside the graphical user interface of Laoss, there's a pull down in the help menu. In the help menu, you can press show Laoss tutorial, and that's the tutorial document, which has about 7 examples of OLED and solar cell simulations, and those are the kind of examples that we play around with in the hands-on session. First of all, yes, we invite you to download the software Laoss from this location, fluxim.com Laoss download, and yeah, put it on your computer, but of course you need to first get on the wireless internet. There is this guest VLAN, it's called guest VLAN, and how to connect. You select this wireless network and then you open an internet browser, and then the internet browser should guide you through the self-registration. And for the self-registration, you should enter a phone number, I think, where on this mobile phone you should receive kind of code, a code to register yourself for wireless. So that's the way it works. If you have problem with mobile phone and so on, we also have a memory stick where we could share the simulation software on the memory stick instead of download, maybe. Would you like that? Maybe you can copy it here on this first. Okay, so the title of this presentation is Large Area PV and OLED Simulation with Laoss. So it includes both application fields, OLEDs and photovoltaics. And I would like to thank all the authors listed here which have contributed to the development of the software and also to several case studies. So Stefan Altazan has contributed a lot on the development of this. He is a physicist, and Roman Hierstand is here. I just introduced you. He's a software engineer. Then there's Christoph Kirsch, who is a numerical math expert who helped with numerics. Matthias Diethelm, Lieven Penning also have contributed, and Lydia Stepanova, she's in charge of the optical part of Laoss, which you will see maybe for the first time today. And then, myself, I'm not very experienced with the software, but I will nevertheless try to show some exercises. but I hope to understand the motivation. So that's the outline of the talk. I will start with the motivation first, and then we go into electrical module, because the software is split in 3 parts, or it has 3 core parts. One is electrical module, then the second one is the thermal module, and finally the optical module, which is not yet released, but we are releasing this soon. That's the new module that allows us to simulate some optics with a ray tracing algorithm. And the electrical module here, after discussing the electrical module, we will have some first introduction to the software and some first exercise. So the overview, just want to mention that this Laoss software came about 2 years ago. We released this software. So it's one of our 2 simulation software products. And you can imagine that, okay, maybe you know that we have this ZFOS simulation software for one-dimensional optics and one-dimensional charge drift diffusion. This software can nicely complement the PIOS measurements to actually analyze the measured data with simulation. So we call this link SPI, ZFOS PIOS integration. And you can imagine that in the future we may also want to couple the Laoss software to some other products here as we go on. So what are the issues with OLED and PV research? For why do we consider simulation as a helpful tool? So one interesting problem that arises in high-resolution displays is the electrical or optical pixel crosstalk between neighboring pixels of a high-resolution mobile phone, for instance. You may end up with central pixel turn on, but the neighboring pixels also are emitting some light as well. So that's called pixel crosstalk. That's a challenge. That can be a challenge as the resolution gets higher. And another challenge for OLED lighting is that if you want an OLED lighting panel, you want it to be uniform in luminance. So this should be uniform luminance. And in order to achieve this, you should have a uniform potential distribution across the OLED panel. And our software Laoss helps to design the shape, but also define the required electrical conductivities of the electrodes to get uniform emission. And then for photovoltaics, typically you start out with research cells which are very small, but then as you want to upscale to larger areas, you need to connect several cells in series or in parallel. And then the question is how to choose the right shape of the cell, how to interconnect the cells. And this example here shows that you have JV curves for a fixed total size of PV, but then you can vary the number of cells you connect in series for the given total size, and then you can have all kinds of JV curves, more voltage or more current, depending on the splitting into cells. But these are examples that you will see more info later on. And finally, this is an illustration that there is a lot of freedom for fabrication for printed organic photovoltaics, maybe later also printed OLEDs. But if you can print, then you can imagine to print a funny shape of solar cell, and it would be nice to simulate also this particular solar cell shape and make sure that each subcell has the same current. So in terms of OLEDs, the problem is that the JV curves of the OLEDs, they are quite steep, right? This can be a really steep JV curve above the turn-on voltage. And if you imagine now you have a large OLED panel and the voltage drop between the 2 electrodes just slightly varies here, then you will have a lot different current density, and also in relation to that also a different light intensity. So it will be a non-uniform device. So the challenge is to improve conductivity while maintaining transparency. and that's of course a trade-off. And with the simulation tool, you can play with this trade-off. And here are some examples of an OLED panel from Osram, which has the honeycomb metal grid that illustrates that indeed you can apply metal grid to make it more uniform, the emission. And in our software, we can simply select the predefined geometry, in this case honeycomb geometry, or we can also import CAD drawings of fancy solar cell shapes and then calculate the JV curve. And usually what we do here to compare is we usually input the property of a very small solar cell. So it would be this blue curve with a nice fill factor and a nice photocurrent. But then if the solar cell is getting large and not ideally conducting for the transparent electrode, then we lose in fill factor. And that's the gap we want to minimize here from the small cell JV to the big cell JV. There is a gap in fill factor and efficiency. Now I'm switching a bit between OLED and PV examples. This could be an OLED example where we have a quadratic OLED shape and we apply a voltage on 3 of the 4 sides. And what we evaluate here is a cross-section, the potential distribution in this direction. So on the right-hand side, you see the potential. Without any grid, we would apply a voltage here of 6 volt, a potential of 6 volt on the left, and then the potential would drop significantly to only 3.2 volts in the center or over here on this right-hand side. And as we apply the grid, we see that the potential is much more uniform. So the pictures, of course, false colors are misleading. So these wiggles here are really a very constant value across here, and that's much better than the case we had before without any metal grid. And please don't hesitate to ask questions while I speak. I'm happy to answer questions. This is another example where now instead of just having one voltage applied, we can of course also sweep the boundary condition, sweep the applied voltage. And again, this would be a simple quadratic OLED example where we feed in a JV curve, which is simple analytical Mod-Gurney law, so a quadratic JV curve. And we can plot this input, the red curve here. That's the JV law we put in. And so it's current density divided by current divided by area. And afterwards, if we do the large OLED simulation, we can also evaluate the current and divide it by the area. So we can again compare what is the ideal JV curve of this size of OLED and how does it look like if we don't add a metal grid. So the green line here, that's a kind of poor JV curve. So we have obviously to reach a certain current density, we have to apply more voltage, and that's because the series resistance in this transparent ITO adds a voltage drop from the center to the boundary of the OLED, and this voltage drop is we have to apply in order to get the same current. So we're kind of shifting away from the ideal JV curve because the electrode is limited. But these several examples, the green one doesn't have any metal grid, but then we can apply a 1D grid, means just in one spacing in one direction we apply grids. And the last example, 2D grid, means we have a grid in like this across like a checkerboard grid on the OLED. So only if we apply a 2D grid, we can approach the theoretical input law of JV much better. Okay. Now, this is all relevant in real OLEDs, as you may have looked at in OLED lighting panels from LG Chem, LG Display in Korea. They fabricate OLED lighting panels and they indeed apply a metal grid, as you can see here, and they add a light scatter foil to the metal grid. Helps to get uniform potential, and the scatter foil increases the light out coupling. Now, for a more quantitative example, I've already shown an example before, but here is again a quadratic OLED. We apply a certain voltage of 6 volt on the sides, and in the center here we would have only a strong drop of potential, so only 5.1. And now in the right hand side we apply a metal grid. You can barely see here the rectangular metal grid applied, and that leads to a more uniform value distribution of potential. So we have only a small voltage drop from the boundary to the center. And there's a previous publication for a while ago from the Nates group. They have fabricated such an OLED or measured the luminance inhomogeneity in this OLED. So the luminance was plotted across the OLED in this cross section, and you see that our software in blue lines can reproduce also this shape. So this was a luminance profile measured with a camera. So you can imagine that with the software we can also show a map of the current density, so the vertical current density, and that would translate in ideal case multiplied with considering the efficiency of the OLED gives us a luminance map, so we can compare with the luminance of the OLED. Now that was a bit of motivation for OLED lighting. In terms of solar cell in PV, the researchers start with small cells, and they want to upscale to larger scales. And by just taking a single cell and just increasing the lateral dimensions, you would get a JV curve where the fill factor drops, and as a result, also the photocurrent can be smaller. So there's a loss in fill factor and photocurrent. And in the solar cells, okay, we don't in the OLEDs we had a lot of current flowing above the turn-on voltage. In the solar cells, it's typically you want to operate at the maximum power point, and if you shine light on it, then you also get a lot of photocurrent, and this current needs to be collected in the transparent electrode, and that's where we also have resistive losses. And so the working point will also move as we have poorer electrodes. So let me look at the particular, quite a popular monolithic solar cell design, where we would have, this is a top view solar cell mini module where we have 4 cells connected in series from left to right. So they are elongated solar cells, and there's always the top electrode that goes back to the bottom electrode in this interconnection. I'm sorry, now I don't have the cross-section view for this, but so there is this metal finger one can add such that this metal finger can collect the current which is generated in these yellow areas. So the sun is illuminating this solar cell, and below the metal finger we have a shading effect. So the metal fingers should be as small as possible in order to avoid shading effect. If shading in a solar cell is bad, of course. So we have to find an optimum between the collecting a lot of current, so adding a lot of metal grid, but also minimizing the shading losses. So it's the question is here, what size of finger to choose. And this is already showing you how to apply a boundary condition. So in the software we would apply on the left hand side this gray metal. We would now tilt it in the graph by 90 degrees. We would apply voltage here, and then the green is just a natural boundary condition where we have no current flowing directly from this outside, but the current will be coming from below because the semiconductor layers are below this rectangle. So we need to feed to the software, we need to tell the software what is the JV coupling law between the top electrode and the bottom electrode. So there is, on the one hand, below the metal, we have to use a dark JV, which is this green line. So we have 0 current there, only injection in forward bias. And in the active area, we need to feed an illuminated JV curve. So that's the current divided by the area. So that's input to the software. And yeah, why is this input? This sketch here I will explain later on. That's how the model is made. It needs input law for the current density, how it depends on the voltage drop vertically between the two electrodes. And sometimes it helps to, it can be sufficient to just simulate a portion of the domain, just one section of the whole domain, to have even faster simulation time. So here we just visualize one single finger where we see the electric field, how it is enhanced a bit around the metal tip there. And I think in the overall result here, we swept the voltage to get the JV curve for 3 assumptions of the metal finger width. So if we don't add any metal finger, that's the green line, then we again have this resistive losses. So the fill factor of the green line here, of the green JV, is poorer than the blue case, where we add a thin metal finger. So in the blue case, we add conductivity to the electrode, and the photocurrent is still high because the finger are so thin. If the finger gets wider, like 1 millimeter, then we have a good fill factor, but then we lose photocurrent because we have shading effect. So this shows you the different scenarios. And so these are 3 examples of a sweep. In the software, we can sweep the metal finger width, so we can go from very thin, where we have resistive losses, to very thick, where we have loss due to shadowing. And what is plotted here is the maximum output power, so 160 watts per square meter. That would be the maximum power consistent with the JV curve. So there is a sweet spot, an optimum thickness of the metal finger that gives you highest power of the solar cell. And now switching back to OLED displays, not OLED lighting, but this time OLED displays. We realized that we can use Laoss simulation software also for analyzing pixel crosstalk in high resolution OLED displays. And the motivation here is, for virtual reality applications, the pixel density cannot be higher. I mean, it can the higher the better. So you see that typically nowadays the pixels are such a high density, but still there is a gap between pixel to pixel in the separation area. There is some design rules that tell you that the pixel separation needs to be at least a certain value. And one of the reasons is indeed the pixel crosstalk. So what we observe in a display, it turns out at low brightness, if we turn on all the blue pixels, but then at high brightness we would have a nice blue. But if we would turn down the current density level, then some neighboring pixels would also unintentionally light up, and that gives us a kind of purple-blue. This was actually measured by a PhD student at LG Display in Korea and presented in a poster presentation, and this inspired us to analyze this problem by simulation. So what is happening here, a typical cross-section of an OLED display, we have here an anode from this top emission OLED of the blue pixel, and an anode for the red top emitting OLED pixel. And some of the layers are uniform across several, or actually all pixels. So there is a whole transport layer that covers both of these neighboring pixels, or even more pixels. And only some of the layers are patterned, like the emission layers and the ETL transport layers. So there is a chance that the whole injection layer and the whole transport layer there are common, and that's where, because of the high conductivity due to charge doping, this layer can kind of lift the potential on this anode of the neighboring pixel, and that will lead to a light emission coming from the neighboring pixel. And so what are the critical parameters? Of course, the geometry parameters, density and the layout. Then we need to know the conductivity of these common layers, And we need to feed in for each pixel, or red, green, blue, we need to feed in a current density luminance curve versus voltage. And that's what we did. Actually, Matthias also joined us. He is also co-author of this paper because we ended up publishing this study in 2 publications. And so in this example here, that's now actually a tutorial example. Later on, you can open up this example in the tutorial and run this example and see what are the inputs that we fed here. So we needed to feed the JV curves of red, green, blue pixels. In this particular case, the blue pixel is the largest, the red and green are smaller, and there's certain separations. And yeah, there's a bit interesting that the blue pixel really of course, blue pixels usually have a higher turn-on voltage, so you kind of see that the current increase is later than for the red pixel. You already have a current flowing at lower voltage. And so we have made the assumptions that we just used sheet resistance for the common layers. And so instead of doing a 3-dimensional simulation, we assumed that the common cathode in the cross section can be seen here. There is this gray layer, that's the common cathode, which is kept at one potential of 0 volt here in this case. It's uniform across, but the other electrode is patterned, right? And so in our 2D plus 1D modeling concept, we have this top electrode as the one electrode domain, 2-dimensional electrode domain, and the bottom electrode is a unification of metal plus conductive layer here, conductive p-doped layer. So we have made this assumption that the bumps here, what was shown here as a bump, this yellow bump here is a pixel separation wall, but we kind of simplified and assume everything is flat. And then what do we get as a result? For any given applied voltage to the blue pixel, so the long pixel shown with the red value, that's the blue pixel. It's very confusing. You remember, it's the long pixel so this one has 4 volts applied at the boundary of the rectangle, and these blue-looking red and green pixels, they are dark, or they have a lower potential. So this value, the blue values are 2 volts, and the active pixel has 4 volts. And now what is interesting to analyze is the subdomain current. So each of these pixels in the software, we get the current flowing through these subdomains, RGB subdomains, and then we can plot the different, the active center pixel, that's the blue one, has the most current, but then the neighboring pixels, the red and green ones, they at low voltage, you see here at low voltage, they have a significant contribution of current. And if we define a ratio, the black dashed line is the ratio between the red and the center, so red and blue pixel. We see at low voltage there is this percentage can be almost 10% or 11% at low voltage. So just above turn on, we have very high, 11% high contribution of red light in the display, and that becomes visible as a color change to purple blue instead of pure blue. We can also consider the efficiency curve, candela per amps as a function of voltage. that allows us to translate the JV curves into brightness versus voltage curves. And now depending on how efficient these pixels are, the blue pixel is typically less efficient, so it turns out then that the actual luminance ratio is not 11% red emission, but even 40% parasitic luminance. So the dashed line now is up to 40%. So the red pixels are quite bright compared to the blue pixel. Okay, that was a lot about applications. I think it's time now to dig a bit deeper about the simulation software Laoss. What are the assumptions behind the software? How does it work in terms of workflow? And then we could do some exercise in first exercise. So our philosophy was, okay, there are some finite element software tools out there, general purpose tools, but we wanted to develop something very specific that can address the customer needs in PV and OLED industry. And that's why we developed this, and it's supposed to be very user-friendly, but still having a state-of-the-art FEMS code and solver with a high calculation speed. And we want to have ease of use, meaning we want to allow predefined shapes, typical shapes already predefined, or allow for CAD import, and then also do the relevant post-processing, which a general FEM tool would not do for you, maybe here with everything's ready out of the box. And the concept here is we don't do a three-dimensional simulation, but rather we do coupling of two 2D domains. In each of the 2D domains, we consider conductivity, electrical conductivity, but for the thermal module, also the thermal conductivity. And then we have a separation of the two 2D domains, which represent the two electrodes. And this separation is the semiconductor stack, which is being described by a JV coupling law, current density versus voltage. That's the law we have to import. And yeah, all the red quantities are input quantities, and all the green values, current density and potential, or the luminance map, that would all be a result of the simulation. So we can visualize for a given voltage applied, we can get the potential distribution and also get this swept JV curve. Yeah. Yes, so far in the Laoss software, our philosophy is, okay, we would have the ZFOS drift diffusion as a software to do the numerical simulation, but right now you still have to store the JV file, and then import this JV curve as a result from ZFOS, import it into Laoss. So it can be an analytical coupling law, a tabulated JV curve, and so we have 3 or 4 analytical laws, Mott-Gurney, and some exponential curve like JV curve of solar cell, some Shockley diode models, and
You can also add your own mathematical formula.
oh yeah, that's nice. You can enter an algebraic expression to describe the JV law also with your own model, so that's quite convenient. Yeah. And just a quick introduction to finite element method. So we're solving this conservation law, the divergence of the current in the lateral domain. So this would be the law that we solve for the 2D domain. We have a 2D domain where the divergence of J is not 0 because we have current coming from below. So there's OLED stack below. And then we assume Ohm's law for the current expression here. And then entering this into this equation, we end up in this equation with Laplacian of the potential psi is equal to minus J, and small j is the coupling law. And the FEM method basically is a numerical approximation which takes some shape functions and some coefficients. So we want to make an approximation, the superposition, where we need to optimize the psi I, these coefficients need to be optimized such that the residuum, namely taking this equation, putting everything on one side, we would expect 0, but the R is never 0. It's always a numerical approximation. We want to minimize this R such that this equation is satisfied, right? And one can also, as a user, if you don't want to work with default values, you can twiggle with the solver. You can maybe change the required accuracy. How small is this residuum? And yeah, the coupling laws, that's your question. We have ohmic, Modgurney, diode model, tabulated, and algebraic expression, which is missing here on the slide. Okay. It's also nice that there are two meshing algorithms included, so it's a triangular mesh automatically generated after you define the geometry. Then we have a fully coupled Newton solver. Meaning for electrical and the thermal part, everything together, top and bottom domain, everything at once. And we can import CAD drawings, and you will see there's visualization and post-processing. We have these three modules. And interestingly here for meshing, it's also a mesh refinement algorithm is built in. So if you have a special metal grid line shape where the numerical mesh should be fine near edges, the refinement algorithm will automatically refine the mesh where needed. And so the basic workflow is you have an idea of a geometry. In this case, our collaboration partner from CSM, they had some drawings already from an organic solar cell, which has about 7 solar cells connected in series, and we just imported for one solar cell. We imported this one leaf here. This is the shape of one leaf here. And then our Laoss does the meshing, where we get a mesh inside this custom shape, and then the user enters the JV coupling law between the two electrodes, top and bottom, and then the user can run the software, and we get a potential distribution all across, or in this case, it's actually a device current flowing in this top electrode. Of course, then you can reiterate and improve the shape or change the material parameters until you're happy. So, until you get the best performance. There are some predefined layouts, so you can import a CAD file, which is DXF, but you can also just select from one of the predefined geometries. For instance, this is the metal finger that is popular for thin film PV modules, where the width of the finger can be modified. And the metal strips, either vertically or horizontal or in both directions, that's possible. And we also have a honeycomb pattern as a predefined shape. For those who want to draw your own geometry in CAD, we didn't invent a CAD drawing tool, but we can now suggest that you use free CAD software like this one, LibreCAD, which is a 2-dimensional CAD drawing tool where you can define, you can draw interactively, and then just make sure to consider some naming conventions that is recognized by Laoss once this drawing is imported, right? Or is it?
It's not necessary anymore.
Not anymore.
If you use the geometry import.
Now Laoss has become more fancy that you can import any CAD drawing and then interactively choose which graphical element is a subdomain, what is the name of the subdomain, and later on you can refer to this subdomain and give it physical properties. So that's all included now in Laoss. So you just need it for drawing this CAD. Basic operations, so that's the main window. When you open, you get these project properties on the left. This is the first tab where you define the geometry, either importing or select something. And then you can run the mesher just to have a preview of the mesh. And then the second tab here after geometry and meshing, there's electric coupling. That's the dialog where you can enter for each subdomain, so you have electrodes, you have transparent area, inactive area, so for each subdomain in the 2D electrode, you need to specify the JV coupling law. And finally, you just press this play button, that's the run button, which will calculate the solution, and we get the result here. So that's a very quick 3-step workflow. Later on, you will notice that there are more windows to care about. And I also would like to mention that there's choice to simulate coupled electrodes or single electrodes. Quite often in OLEDs, or always, always, we have an electrode which is highly conductive, like a uniform metal sheet as a common cathode, for instance. That would be a highly conductive domain, which could be simplified as ideally conductive, meaning that it's equipotential, so this potential would be applied on the whole domain. And then only the other electrode here, shown up here, would be the one with limited conductivity, where we have non-uniform potential. So it means we can get a speed up if we go from this generic case to the special choice of only solving for one domain, but still considering the coupling between top and bottom electrode. So there's a choice you will see in the GUI, single or coupled electrode. So the coupled electrode case, you actually solve both domains, top and bottom, which is necessary if you have poor electrical conductivity in both domains. And in terms of post-processing, we can visualize also cross-sections of potential, for instance, in addition to the JV curves I've already shown. And then you can select several or add, use this keep button to keep the previous selection, so you can make direct comparison of profiles. That's also useful to compare the total current from the simulation, in purple, to the electrode local JV law, which is the one you had specified. As an input, you have to specify the electric coupling, right? You enter the JV, you import it. So that's the red curve here. But after the simulation is finished, you can, with a right click in a pop-up menu, you can copy the result into this graph here, and then you can directly compare the output current density to the input current density. And if there are resistive losses present, then you see a difference. If you have highly conductive electrodes, then there would be little difference. Okay, now I will maybe suggest to make a little exercise instead of presentation. Please, try to open your Laoss version.